Okay, so new topic for today. We're going to talk about line integrals. You may be thinking, wait a minute, we've already talked about line integrals. We did a bunch of stuff with line integrals. And then you may remember I gave a disclaimer and pointed out that I really like to call these scalar line integrals. The kind of integrals that we talked about in the past were scalar line integrals. Because we were looking at integrals where the integrand was a scalar, where, this is going to sound silly, where the differential was a scalar. Well, of course it was. Right? Every differential we've ever seen was a scalar. So anyway, we're going to see a new kind of line integral today that I feel should be called something different because it is a really fundamentally different kind of question that it addresses, and I think a pretty fundamentally different thing. And there's different points of view on that. But anyway, so this is called line integral of a vector field, or I like to abbreviate that sometime to vector line integral. Okay, so here's the idea, and again, I'm not going to write down the definition immediately. I'm going to try to, sort of work up to that with with an example. Remember, with single variable integrals, the question that sort of motivates single variable integrals is area under a curve, or mass of a one-dimensional rod, or physical examples, geometric examples, and you think about chopping it up and what kind of Riemann sum does that eventually give you. Likewise, with double integrals, there were motivating examples. With line integrals, scalar line integrals, there were motivating examples. Here's the motivating example that I want to talk about, and it goes all the way back to chapter 12, work. So I hope you all remember work. If you haven't had a physics class before, no problem. Work is just a measurement of how much energy it takes to accomplish a task. It's pretty intuitive. More force, more work. More distance, more work. Right? And here's the formula that we kind of sort of derived. I'll say motivated. Back in chapter 12, notice that the dot product keeps track for us of the extent to which the force might not be in the direction that's actually of the actual displacement that you're making. Okay. All right, so this is an improvement, a significant improvement over the formula that those of you who took high school physics, over the formula you saw in a high school physics class, because of this dot product being in there, because of thinking about force as a vector, not a scalar, right? Thinking of displacement as a vector, this is all much more natural than the way they do it in high school physics. But it still has a problem. This assumes that the force is constant over the entire task, and it also assumes that the displacement is over a straight path. Well, both of these are highly implausible. Right? In most things that we do, how often do we go in exactly a straight line? How often is the force actually a constant? So here's a harder problem then. Let's suppose that our forces that we're keeping track of are highly non-constant. See how these vectors are not the same. Right? Well, that means our above formula doesn't fit with this. What if we're not going in a straight line from starting point to ending point, right? If we were going in a straight line, then we could just call that the displacement vector, and that one thing and tells me everything I need to know about this process of moving from there to there. But what if I don't? What if I am instead doing that? That might not be the same amount of work. Maybe it is, but we certainly shouldn't assume that it is. Okay, so this is the problem we're going to consider now. What if you're moving along a curvy path, exerting a non-constant force? How do you compute the total amount of work? Okay, now this being a calculus class, you could probably guess the very first thing that we're going to do, as I like to describe all of the integrals that we've done so far. Chop it up, add it up, right? So this applies to every integral we've done so far with some sort of a domain associated to some sort of a quantity, and if you chop that domain up into little bitty pieces, if on each little piece, if the problem becomes, look, it's real easy on this little piece, right? If you can solve the problem on that little piece, then just add it up over all of the pieces, right? Now this assumes several things. Among is that on each piece, that the quantity that we're computing on each piece, when you add it up, does give you the total. So that sounds like a weird thing to say, but the quantity has to be an accumulating quantity. So mass, my favorite example, is an accumulating quantity, because if you have a certain amount of mass, if you chop it up into little pieces, it really is the total mass is the sum of those little pieces of mass, right? But if you have a solid, and if you're interested in the surface area of that solid, the surface area of that solid is not the same as if you chop it up into a bunch of pieces and look at the surface areas of all the little pieces. That does not add up to the surface area of the whole. Right? So not every question in life is a question about an accumulating quantity. Right? So that is an assumption that we have to make with the chop it up, add it up strategy. So anyway, is work an accumulating quantity? And I pose, yeah. The total amount of work, if you were to measure, how much gas does your car burn in driving along this road, perhaps? Right? Well, the amount of gas that your car burns on this little piece of road, plus the amount of gas that your car burns on the next little piece of road, etc. It's accumulating. It's clearly an accumulating quantity. Okay. All right. So we chop it up into little pieces. On each little piece, such as that little piece there, notice that that little piece of curve, it's not exactly straight, but it's approximately straight. Right? And the force that I am exerting, it might not be exactly constant. It might be ever so slightly different on the other side, but it's approximately constant. So we're assuming that we have a nice curve, nothing weird. There's anomalous, sort of weirdo curves that we're not going to worry about. And likewise, that the vector field is reasonably, so continuous is what we need in the vector field. But anyway, okay. So here's the on each little piece. Then let's look at this little piece of curve. Color on that little piece of curve. Not exactly straight, but it's pretty close. That little piece of curve is very closely described by this vector that we motivated that vector a long time ago, the dx vector, velocity times dt. We motivated that when we were writing down scalar line integrals. That very closely represents the displacement as we move along that little piece of curve. The force, again, not exactly constant, but the force is, again, assuming that it's approximately constant along that. We now have on this little piece, an old familiar question, namely, on an approximately straight piece of curve with an approximately straight force, how much work does it take to move along that displacement? Well, here you go, simple formula, right? The force dot the displacement. So F dot dx. And then no surprise, we're just going to add up over the entire curve, right? So the total force, the total work is the sum of these little pieces of work. That's how accumulating quantities work. And don't forget we have our formula here for dw. It's F dot dx. And there we go. I mean, this is a shorthand, of course, but this is a pretty reasonable shorthand for a Riemann sum representing how we would compute the amount of work that it takes to move along that curve. How we doing? Everybody on board? Chop it up, add it up, right? Okay. Okay, so let me say a couple of quick words. So this is our new kind of integral. This is called a vector. This is what I like to call a vector line integral. And notice, as promised, this integrand is not a scalar. That's not like a density or a, height or something like that. This is a vector integrand. That's weird. We've never seen that before. Okay. Notice also, as promised, our differential. Right? And I was kind of joking about this earlier. How could a differential be a vector? There. That's how. Right? The vector differential, the position differential as you move along the curve. Right? That's a vector differential. So this kind of an integral, it's a line integral because look, we are moving along a curve, right? There, our domain is a curve, so I mean, we're going to recycle the term line integral, but it is a fundamentally different kind of construction. It addresses very different kinds of questions, right? And so I think it deserves a different name. Okay. All right. And here we are again, brand new kind of integral, the looming question, how do we compute them? Right? It's all well and good to make abstract talk about how, complicated application. Let me write down some abstract notation and then feel really good about myself. Right? But until you can compute it, it's not clear how beneficial that is, right? Okay, so how do we compute these things? How did we deal with this when the last time we saw a line integral? We recognized that part of the problem is that this domain is dimensionally awkward, right? That domain is it's a one-dimensional thing in a 2 or 3-dimensional context. So is this a triple integral? Is this a single variable, Calc 1 integral? It's not clear how this fits in with any of those techniques, and it doesn't, right? So we're going to do pretty much the same thing that we did with scalar line integrals. We're going to take that curve that is dimensionally awkward, and here it is, right? Dimensionally awkward, one-dimensional thing in a two-dimensional world. We're going to view it as an image of something more desirable, such as a nice, good old, plain old interval on the t-axis, right? A one-dimensional domain and a one-dimensional world, Calc 1 land, right? And then we do a pullback, just like every other pullback we've done. Okay. So that's our strategy. And details, right? You got to work out the details. Anytime you do a pullback, there are details to be worked out. The good news here is we've already worked them out. Everything that we need to do this pullback, we've already figured out. Specifically, what do I need? Look at this, what we've got going on here. Well, for one thing, this function is a parameterization. We've made that realization in the context of scalar line integrals. So we know how to parameterize curves. I mean, it's annoying sometimes, right? There's detail. But the concept of parametric curve, we're good. The other thing that we need to know is how do I compute that thing? Right? This position differential, the dx vector. Well, we have a formula for it. It's v dt, no problem. All of that is in terms of t, right? Velocity is a function of time. dt is in terms of time. So the only pullback formula we need is already right there. Everybody good? Now, one thing that used to bug me, let's see, do I have an example next? Yeah. Okay. So one thing that used to bug me about this formula is I looked at, okay, well, dx is v dt, okay. And then f, the vector field is, well, it's a function of position, but position's a function of time, so, plug in and everything. But what I always found uncomfortable was, where's my stretching factor? Aren't you supposed to stick in a stretching factor for, good measure or something? Right? I thought that was, I don't know, I felt like it was missing. So let me just point out, it's easy to see where the stretching factor is. It's actually already in here, right? The stretching factor is a size. How much size, how much is this magnitude bigger than that magnitude? And, well, it's part of that vector. It's part of the velocity. Specifically, the velocity is magnitude of the velocity times the direction that the velocity points. And there's your stretching factor. Right? That's it. It is sitting inside of here. So I think I actually did this on a test a long time ago when I was in college. Don't stick in an extra stretching factor, right? It's already in there. It's part of the velocity vector that we're now dealing with as a vector. Okay. All right, so let's get our hands dirty and do an example. By the way, make sure to memorize this formula. It's really important. It's going to, every time you do a line integral of a vector field, that's the pullback formula. So make sure to know how to do that. Okay, example. Let's suppose that I am walking. Let's see here. Let me color code this well. We're walking counterclockwise along the top half of the unit circle. Okay, so picture Here's the top half of the unit circle. We are walking, now notice, counterclockwise. That matters. Right? Of course, walking one way along a path is not the same experience as walking the other way along the path. Downhill is not the same as uphill. Into the wind is not the same as with the wind. Okay? So we're walking counterclockwise. And then let's see the force that we're dealing with. The wind force that we're dealing with here is that. So we've got a force and we've got a path. Look, you could take the point of view of parameterize the path, plug in the force, and take a deep breath and plug and chug. And that's not far off from what we're going to do, actually. But there is a little detail that we need to worry about, and that is about the direction of the force. So if you haven't had a physics class, then you might not have seen the following before. If you have, I'm sure you have. But so we can talk about the force here. How much does this pen weigh? There are actually two forces in play right here. There are two exactly opposing forces. Said differently, there are two forces that add up to zero. I know there's a total of zero force because there's zero acceleration, right? This pen is not hurtling toward the ground. Okay? So the two forces are, well, there's gravity is pulling the pen down, right? But I am pushing the pen up, right? So when you're doing a work calculation of these two forces, you have to decide which one is the one that you actually want. Do you want the down force or the up force? Or do you want the into the wind force or the against the wind force? You got to think through which one you actually want. Then you also have to think through, wait a minute, which one was I actually given? Right? And you cannot assume that they will always be the same. And in this case, they are not. So in this case, wind is exerting a force on me of an amount that I'm given. The question is about how much work do I exert? Right? So I was given one force, and I'm given so the wind's blowing in my face. I was given the force that the wind is applying to me, but I want to know how much work do I exert? I exert work I may exert a force to oppose the wind that's blowing on me, right? So if you're interested in work that I exert, then we got to look at at force that I'm pushing with in the calculation. Okay, heads up, right? It's just a minus sign. It's pretty easy to deal with that, but you do have to. It's your responsibility, right, to figure out that this force that the wind is exerting is the opposite of the force that I'm exerting. Thus, you got to stick in a minus sign. All right, everybody on board? Easy mistake to make. Look at the language. Think about the givens and just make the right choice. Okay. If you have any questions about the physics of that or whatever, come talk to me. It's fine. Okay, so everything else here is plug and chug. It's very plug and chug. So the force was given. We'll get to that in a moment. Now I do have to parameterize the curve. I guess I have to come back up here. So here's my curve. I've got to parameterize this curve that goes counterclockwise around the upper half of the unit circle. We know how to do that, right? That's a whole cosine comma sine thing. We talked about that a long time ago. So there's my parameterization. Notice it's just from 0 to pi, because I'm just doing the upper half. Okay. Formula back here, I'm going to need to know the velocity, eventually, of the parametric curve that I'll be using. So I'm going to have to take a derivative to get that velocity. Here you go. All right, there's the velocity. And now it's really just a matter of plugging in at this point. So, let's see here. Let me zoom out for visual purposes. Okay. The force that I am exerting is negative F. Right? That's the... Okay, I'm not sure why it won't let me I like that. Oh, there it is. Oh, it was just slowed down. Okay, that was weird. All right, let me do that again. Here's the force. That's the force that I'm exerting. Right? The F that was given, namely the force that the wind is exerting, is y comma negative x. Right? Don't forget the minus sign. Slowly and carefully, by the way, is a big trick on these. Don't sort of write it down too fast and, carelessly and then inadvertently get some minus signs wrong. Okay. Right, so let's see here. dx is velocity times dt. Here's the velocity. Yeah, everybody good so far? What's the deal with the y comma x here? Let's how do I deal with the y comma x? Don't forget x and y are in the parameterization, right? So y is sine t. Don't forget that minus sign. Okay. Likewise, this x here, that's being multiplied by two minus signs, is cosine t. Okay, so that's just plugging in is all we did. And notice we've got an integral. It's everything in here is in terms of t. Furthermore, we got lucky with this one, and it happens that the integrand simplifies dramatically. That integrand is just 1, and so easy integral, and bam, done. Yep?
Is your x vector always going to be x comma y, which then you parameterize?
I mean, that's highly conventional, right? I mean, if you're dealing with x's and y, if the space that you're looking in is if that's your x and that's your y, then yeah. But I mean, if you're in a weird sort of phase space or something, and if that's p and this is z or something, then choose accordingly. But I think it's a good idea to pick a coordinate system, right? Make some standard choices about what you want your variables to be, and then stick with it. Yeah, absolutely. Yep.
If we're not given a circle as the path, how do we parameterize?
Yeah, so parameterizing is a trick. We're going to talk more about that as we go along through the course. The one example that I gave not long ago was the graph parameterization. Remember, so if what you're looking at is a graph, that basically gives you a parameter. Let the input variable be your parameter. The output variable then has to be what it has to be, and there's your parameterization. Yeah, right. But we'll see some other examples. Yeah. Okay. All right. Okay. Here's another example. Zoom back in. So what if you are instead walking clockwise? Now, there's several different ways that you can think about this. I'm going to show you 4 different ways that one might think about this. 3 of which are highly acceptable. The other one, not so much. So I'll let that kind of dangle for a moment. But the first 2 ways to do it are just parameterize your curve. There's nothing really. Who says you can't parameterize a path walking clockwise? So here's one way to parameterize a clockwise path, and that is to observe that if you are going that way, you can just define that angle to be t, right? I mean, if that angle there is t, then you are starting where t equals 0. You are ending when t equals pi. So as t goes from 0 to pi, that will take you right around that curve. Right? Now, okay, if that's t, fine, right? But I need to know then what are the coordinates of this point. I still need to know x and y. In order to understand x and y, I need to understand theta, right? The relationship between x and y and angles is r cosine theta, r sine theta. So I need to know theta. But in terms of t, and easy to see that relationship, right? If t is that angle, then theta is, it's pi minus t. And so notice position is just cosine of theta. Here, let me cosine of theta, comma sine of theta. Nothing's different. It's just now how theta depends on t has been tailored to my needs. Yeah, happy? And then, all the usual, you've got to take your, you've got to apply your angle addition formula. By the way, I hope you all know your angle addition formulas are really convenient. Do you all know the angle addition formulas for sine and cosine? If you're not good with those, if you've forgotten them, or if, as is I think very often the case, if your high school trig classes have told you that you don't need to know those, I think that was bad advice. I think, maybe not everybody needs to know them, right? But Duke Math 212 students need to know your angle addition formulas for sine and cosine. So make sure that you know your angle addition formulas and your symmetries of trig functions. Also really handy. Okay. All right. So that's one way to do that. Now let me show you a different way to do that I don't have on the page here, but I'm just going to highlight my way through it. So this curve that we're trying to parameterize. So that point going around that way. That's what we're trying to figure out. Notice that it is simply a reflection over the y-axis of a parameterization we already know. Namely, it is just a reflection over the y-axis of upper half of the unit circle going counterclockwise. I know how to do that. Right? This one here is just cosine t, sine t. Right? So the reflection then, the act of reflecting over that line, just gives me a minus sign on the x coordinate. So I think that's a really nice way to think about it as well. Super convenient, right? I mean, if you get lucky and it happens to be clearly, obviously, a nice reflection of a parameterization you already know, then okay, capitalize on that. Questions on that one? All right. Okay. Here's a third. I call this 2, but it's actually 3, if you think about it. Is to make a Riemann sum argument, and that is to notice that, look, if you've got some piece of curve, and this picture is highly exaggerated so that it's not 3 lines kind of right on top of each other. But if you've got a little piece of curve there, what is the difference in the Riemann sum of going one way versus going the other way? You're still looking at all the same pieces of curve. The force vectors on those little pieces of curve are still, look, you're evaluating the same force field at the same points. It's all the forces are the same. The only difference is that your dx vector going one way along the curve versus your dx vector going the other way along the curve are exact negatives of each other. Right, so the only difference is a minus sign. Said differently, the only difference is a minus sign in exactly one factor of exactly every term in the Riemann sum. So you get the exact negative of the otherwise answer. Right? I think that's a lovely argument. Understanding how Riemann sums work. Right? So this is something, I hope you all will take this to the bank. It's a neat fact about vector line integrals. If you're looking at a curve, if you compute a vector line integral over a curve going one way, or if you look at the exact same integrand, exact same curve, the only difference is we're going over that curve in the opposite direction. Exact same curve, just retracing your steps going backwards. You will always get the exact negative. Nice fact to keep in mind. So you're welcome to invoke that one. Okay, now let me show you the unacceptable, what I do. Oh, by the way, you can see it right here. Look, the answer was negative pi compared to positive pi going counterclockwise. So that tracks. Okay, so here's the unacceptable. I can't deal with the following. The argument that could be made, let me do this in a better color, is to say, all right, well, look, this point, oh, come on, elbow. This point, I'm just going to call theta that angle, and I'm going to say, well, the amount of, okay, so again, my computer is delayed. There we go. Okay, so the amount of work, that's an integral, and I've got f dot dx And let's see, I'm going counterclockwise. Okay, so I'm going to make it go counterclockwise by picking the counterclockwise parameterization. I'm going to make it clockwise by going instead from t equals pi to t equals 0. Okay. So I've seen students write this down before. Right? Just have the integral go from pi to 0 instead of 0 to pi. Now, let's start with the positive. This will actually numerically give you the correct answer. That's true. The reason it will numerically give you the correct answer is because, well, as it turns out, integrals, when you switch the order of replace the a with the b and the b with the a, right? That gives you a minus sign, and that's also true. But what is that? What is an integral from where I'm defining presumably an integral on an interval? What interval is this? That where the left endpoint is pi and the right endpoint is 0? That's not an interval, right? So that's really, it's not a thing, right? So the way we define integrals is you give me an interval on the x-axis, t-axis in this case, an interval on the t-axis, and you give me a function, and we write down the Riemann sum from that. A related sort of comebacker that students will make sometimes is, okay, well, yeah, but I'm just letting time go backwards. And I'm like, okay, now you really lost me, right? Really? So I'm asking a standard easy physics question, and your solution to the physics question is to postulate about how physics works when time goes backwards. And I'm just thinking, wow, that's really aggressive. Right, and so I think this is a really bad idea. I think the underlying idea behind this, the strategy of letting the integral go from pi to 0, I think it's all highly fishy. I don't believe it. So I'm going to call this not acceptable in Math 212. Time shall not go backwards in Math 212. So keep that in mind. But notice I've given you plenty of other options, right? You've got a couple of different ways that you can parameterize. You can very legitimately make an argument that, look, Riemann sums are Riemann sums, and if you had a minus sign on each term, then fine, right? But I don't like the whole time going backwards thing. Okay. All right. Moving along. So we've been talking about work all this time. Remember, there's different ways to think about vector fields. You can think of vector fields as representing forces. That's the point of view we were taking here. Right? This vector field is representing forces. There is this whole other point of view on vector fields, which is, what if the vector field represents fluid flows? And there doesn't have to be any forces involved at all. Well, what does this mathematical construction mean? Right? How would I make sense out of this? What am I computing if I write this down if the vector field represents the flow of a fluid? Reasonable question. And this is something that, those of you who are engineers, this is something, if you take a fluids course, this is something you'll do a lot with, right? And exactly what you will do with it, we're not going to go into that in this class, but it is a big deal. It's very natural, very believable. So the way we have it written down, we're not really set up to answer that question. So let me show you a quick little change that we can make that makes everything line up just right. So remember, this is our picture, right? We've got our parameterization. We have our curve, and we break it up into little pieces. Blah blah blah. We have our dx vector. Okay. And just a reminder, there's this thing called the unit tangent vector. We talked about that. I mean, it's so long ago, I've kind of forgotten when. I think it was back in chapter 12. I want to say 12.5. Talked about the unit tangent vector. And here it is. There's the unit tangent vector right there. Recall also, we have previously discussed this length of the position differential. We've called ds, the length of that little piece of curve. And at a glance, I think it's a pretty easy buy that dx is ds times that unit tangent vector, right? Think about it. I mean, the dx vector points in the same direction as t. T has length 1. If you multiply by ds, now we've got a vector of length ds. Dx has length ds. So these two vectors here both point in the same direction as dx. They both have the same length as dx. So they're the same vector. And if you don't like the geometric argument, you can just do the algebra. Here's the algebra. So we already know that is true, and of course the vector is a unit vector times the speed. The velocity is direction times speed. Again, old news. Move parentheses around, and v dt, speed times time, is just distance. Okay, so if instead of writing down dx as that, if I instead write dx down like that, then we can just look and see what our integral becomes, right? So dx, now t ds, and move parentheses around again. I'm going to have f dot t ds. Oh, don't forget, if you're taking a dot product in the direction of a dot product with a unit vector, that computes components, right? Again, flashback to chapter 12, long ago, section 12.3, I guess it is. Yeah, 12.3, 12.2. Anyway, long ago. And here's a nice interpretation. This is just a rewrite of our same exact vector line integral. Exact same vector line integral, interpreted differently though. And what it tells you is, something that makes sense in the context of fluids. If that's the fluid velocity, or whatever else, in whatever way you're using a vector field to represent a fluid, this just says to what extent is the fluid flowing along the curve at that point. And so the idea, and this is just a little bit of a hand-wavy argument I'm going to leave you with. If the integrand is how much does the fluid flow along the curve on a little piece, then the integral says how much does the fluid flow entirely along the curve? To what extent does the fluid flow along the entire curve? Now, this is not a familiar physical notion. Funny thing about how you associate concepts, if the thing that you write down happens to be something you already have previous intuition for, then you say, oh yeah, of course. Well, that's this thing that I already have an intuition for, right? And if it's not, then there's a temptation to say, okay, well then why do I care, right? So this is not something you've previously seen before. Nevertheless, it still makes sense to talk about it as something that has a physical, something sort of a natural physical interpretation, even though that's not something you're previously familiar with. Okay, so a little weird. All right. Okay. Every so often you get lucky. Life is good sometimes. So let's look at this example. This would look like a hard problem. Suppose I'm interested in computing this line integral here. And the curve that we're dealing with is described in a weird way. Right? I'm going to describe the curve, how I move, by telling you that the curve is on the unit sphere and is therefore moving. I can describe its motion by how phi and theta change with time. So rho is given. Rho is 1. So with phi and theta as functions of time, then I've got position as a function of time. And you could plug this into the spherical coordinate formulas, and you could write down a horrendous formula for x, y, and z as functions of time. So, right? Yikes. And then the vector field that we want to do a vector line integral of is given right there. Notice that our vector field is a scalar multiple of the position vector. Our position vector is that. Right? So if the vector field is a scalar multiple of the position vector, well, then it's going to be pointing kind of like that, like I have drawn there in the picture. Okay, so if you were to brute force this question, it'd be unthinkably inconvenient, right? Just intractable, probably. Okay, so here's the easy way to do it. Like I say, every so often you get lucky, and that is to look at the picture and just notice that, spheres have this wonderful feature let's see, I need a different color. Here we go. We'll go red. The position vector is always perpendicular to the surface. That's just, again, spheres have these nice symmetries. So the vector field is perpendicular to the surface. Whereas, by comparison, my velocity vector, or I can even say my position differential there, the curve is confined to the surface, and so therefore my tangent vector, my dx vector, I circled the wrong thing, sorry. My dx is always parallel to the sphere. Sorry, this was supposed to be that one. So what I've got here is an f that's always perpendicular to the sphere, a dx vector that's always parallel to the sphere, and therefore f and dx themselves are always perpendicular. And so this dot product that I'm interested in, again, this is a horrendous expression that I've got written down up here. But f dot dx, we're looking at a dot product of two things that are perpendicular. Every term in this Riemann sum is 0, so this integral is 0 by the symmetries of the sphere. Yeah.
Relating this back to work, does that mean since the force isn't in the direction of the displacement,
yeah,
there is no work? That's
a fine physicsy way to think about it. Yeah, absolutely. So you might think of this as maybe the force. Maybe the F there is representing, how hard do you have to push to keep you're pushing something around on a road on the surface of the earth, as roads tend to be, right? And you're applying a force to keep your thing from hurtling toward the center of the earth. How much do you have to exert? Well, not much, because the cart that you're rolling it around on is doing it's actually holding it up. You're going that way. You're exerting a force that way, and so it's no work. So you think of this, a nice metaphor for this would be, imagine greased rails, right? Just make a railroad system where that purple path is followed by rails, and grease them up, right? And put it on a little railroad car with nice bearings. Right, and just give it a smallest little shove, and it will just slowly move right along the greased rails and cost you 0 work. Yeah, right. Okay. Alrighty. Okay, so this next couple of pages is sort of an odd little discussion, but this has got to be done. So I'm going to define technically a new kind of an integral here, but it's not going to look like it. It's just going to kind of happen. It's going to sort of fall in our laps. Anyway, I apologize. This is weird. So don't forget, we're talking about little pieces of curve. There's our little piece of curve. We're describing our little piece of curve with a vector differential, dx. And, we know how to write dx. It's v dt. And it's fine to write dx as v dt. That tells you everything you need to know, and you know how to compute that. And what we never got around to earlier in this lecture is writing down, what are the coordinates of dx and what are the coordinates of v dt? Well, here they are. Obviously, the first coordinate of, how much does your position change? The first coordinate is how much does your x-coordinate change? Right? The second coordinate of how much does your position change is, how much does your second coordinate change? Right? So calling the coordinates of the dx vector, calling them dx, dy, and dz, I think is really satisfying. What else would you call them? That's what they are. I mean, the coordinates of the dx vector are how much do those coordinates x, y, and z change over that little piece of curve. So the notation is extremely plausible. And then I'll just remind you super quickly that there's our formula for dx as in terms of t, and here's our formula for dy in terms of t, and likewise dz. Okay. All right. So real quick, I'm going to skip over that and just come right down to the punchline, and I'll come back to what I just skipped in a moment. Fine. So we have our formula here for the dx vector. Again, kind of weird to write it like that, to write it in coordinates, but we could do that, right? And then likewise, here's your vector field. Now our vector field is going to have some sort of coordinates. It's got, I don't know, you can call them F1, F2, F3, but it's a persistent convention to call them P, Q, and R. There's nothing magic about that. It's just, I don't know, somebody made an arbitrary choice there. So anyway, we're going to use P, Q, and R mostly in this class. But just be aware in some context you'll see them called F1, F2, F3, whatever. And then don't forget we are doing a dot product here, right? So that is one of the things about vector line integrals is that is a dot product. And notice you could crank out the dot product, right? That dot product has 3 terms, and you could just write them down. So PDX, QDY, and RDZ. Again, strange though it may seem to do that. And so, lo and behold, we have falling into our lap now some notation that we've never seen before. This is all brand new and weird, right? Let me talk first about how weird this is. This thing here by itself, it's over a curve, so this is a line integral. All right, let me just look at just this one. It's a line integral over a curve, but the differential is not ds. We're not multiplying by the length of the piece of curve. This is not a scalar line integral. It's also not a vector line integral because it's not a vector and a dot product. So this is a third kind of line integral. This is what I like to call a coordinate line integral. It's a coordinate line integral because, again, it's based on looking at what you can see right here, a coordinate differential and the corresponding coordinate of the vector field. So I think the terminology it's pretty natural. And again, I can write this down just to kind of motivated by that notation there, but we really should write down a definition. And so just so that, for the sake of completeness, here now is my definition of what does it mean, if you have a scalar valued function and you want to do a line integral over some curve dx, the definition is, it's exactly what it sort of has to be to make the above calculation work. Namely, it's exactly what you would think. Okay. All right. So that's what it is. These are what coordinate line integrals are. And let me pick on them a little bit. When we wrote down scalar line integrals, I started with a motivating example: mass. We've got a rod bent around, wire bent around in space. I want to compute the mass of that thing. That's natural. That's physical. And we wrote down scalar line integrals. Vector line integrals. We started with a motivating example: work. Right? We want to compute the amount of work that it takes to move along drive along a road or move along a curve in some form or fashion. So again, natural motivating example, and that motivated this kind of example. So where's the physical motivating example for that? I didn't give you one. Because there kind of isn't really a good one. It's just notation. Right? And that's unsatisfying, and I don't really like it. Against very reasonably, students are always looking for, but what does it mean? And I'm not going to have an answer for you on that. So it's just notation, right? Think of this. By itself, it doesn't really mean anything, but this is part of a trio, which is an alternative notation for a vector line integral. Now, I do want to defend it very, 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 very quickly. There are some very good things that you can do with this notation. It's not a bad idea notation. It's a very powerful idea. Super powerful idea of something called integrals of differential forms. It's great. It's just we're not going to do any of that in this class. Right? So the other thing you should know is it's in common use. A lot of people use it. And weirdly, people will use it even when they're not actually doing those powerful things. So in the context of Math 212, I think it's just weird. I mean, which one of these notations do you like better? I like the compact one that has the physical interpretation as opposed to the mysterious, awkward one. That's the personal preference. Right? Anyway, but again, I have to mention it. You have to be aware of it. This is out there in the. It's your future. You will experience this notation. I just wanted you to know that it's there and what it means, and we're not going to do that much with it. See y'all later. Have a good one. Oh, and stick around for homeworks if you have a moment.